so that everybody that can't be on right now can watch this later. So we'll go ahead and go through the slides, and then we'll talk about specific questions that you all have. So kind of similar to what we did last time, I'm going to go through the slides really fast. Let's see, I want to share my screen. There we go. So you should be able to see the slides there, or at least the first page of the slides. And we'll go through these really fast, just very broadly pointing out this is an important topic, this is not something you have to worry about, this is something that will definitely be on the exam, and here's how I'll ask the question, things like that. So I know that this is going to be very, very rapid, but we'll have time afterwards to come back and go over that stuff, go over more specific questions you might have. So the first topic here from Chapter 4, which the exam, by the way, is 4, 5, and 9, are the chapters for this exam. Hopefully everybody realized that, because that was in the Blackboard unit list there. Hopefully you're going by the unit list and not just reading from one chapter to the next. Chapters 6, 7, and 8 all really work well together, and Chapter 6 is ginormous. There is no way that I could have an exam over 4, 5, and 6. That would probably be half of the material in the whole class, would be 4, 5, and 6. So I've split it up a little bit differently. So 4, 5, and 9 are the chapters for this exam, and we're going to start here in Chapter 4 with I believe it was balancing, yes, balancing equations. You do definitely need to know how to balance an equation. That will be a question, or maybe even two. It's actually been a little while since I wrote this exam, but I think it is 2 questions on the exam. I think there'll be 2, maybe even 3 equations that you will have to balance on the exam. So be sure you know how to balance an equation, and if you would like to review over that later, we can do that as well. Solubility was the next topic that we went over, and so this is the idea of when you take 2 solutions that have 2 different ionic compounds mixed up in them, and you mix them together. Sometimes ions from one solution will find ions from another solution, and they will form an insoluble compound. And so it was talking about how you determine if an insoluble compound is formed, how you write the equation for when that happens. The main thing that I'm looking for here is the ability to recognize, number one, what molecules are soluble and what molecules are insoluble. So if I remember correctly, there were 2 styles of questions that I put on the exam, and these will be on the exam. This solubility concept is on the exam. I believe one style of question was just, here's a molecule, tell me if it's soluble or insoluble. And I think the way those were worded were as a true-false question, where it was just, this is soluble, you know, and just naming molecules and saying that it's soluble. And so then you would tell me, true, it is, or false, it is not. I think that was the way that I wrote those, just because it's the easiest way of writing those. So you should be able to essentially use this table to determine if a molecule is soluble or not. And if I remember correctly, the other style of question was something along the lines of what we did here, where we said, here's 2 solutions, tell me if something insoluble is formed, and tell me what it is. So give me the formula or the name. Again, it's been a little while since I wrote the exam, so I think it was the formula that I asked for. So here's 2 different solutions. If something insoluble is formed, what is it? So I don't have you writing out whole equations, similar to what we did here in the in the practice problems where we said we have this reacting with this, and what are the products that are formed, and balance the equation. I don't have you doing that just because there's not a really easy way to do that in Blackboard. It would end up being really complicated, and you'd spend way more time than you should just trying to get all of the subscripts and superscripts and everything correct. So I couldn't come up with a good way of doing that. So there won't be any writing out of entire equations, but you should be able to determine what's soluble and what's insoluble, and if you mix two things together, will it form something that's insoluble? And if so, what is that? What is the molecule that's formed? The next thing here is acid-base reactions, and for acid-base stuff, I'm just looking for the basic understanding of what acids and bases are and how they react with one another. So that basic understanding would be essentially acids in solution form H+, bases when put into solution form OH-, and when they react with one another, they neutralize each other and leave behind some kind of ionic salt. And that's really it. That's all that I'm looking for here. They neutralize each other to make water and some kind of a salt. So just the basic stuff there, not a whole lot from acid-base. Redox reactions. This is again something that will definitely be on the exam. So you do need to know, first of all, how to identify when oxidation and reduction are occurring. And that is governed by these rules, if you remember. I know it's probably been a week and a half or so, maybe a little bit longer since you looked at these rules, but so this is because this is at the beginning of Chapter 4. Going through these rules and determining what the oxidation number is for different elements in a molecule, and then using those oxidation numbers or oxidation states to determine if an atom is oxidized or reduced in chemical reactions like these. So, like I said, this definitely will be on the exam. The way that I ask these questions is kind of similar to what I did with the solubility, in that there's two different ways that I do this. There is, first of all, just here is a molecule. Tell me what the oxidation number is for all the elements in the molecule. So there'll be at least a couple of those, where I just give you a molecule, and I think the way that I did those was like a fill-in-the-blank style question, where I would give you the molecule, and then down below there was a space to put the oxidation number for each element in that molecule. And so you would just give me, so for example here, if I gave you CS2, down below on the question there would be a spot for carbon and its oxidation number, and a spot for sulfur and its oxidation number. And so you would put +4 for the carbon and -2 for the sulfur. So there'll be some questions like that. But then there will also be questions more similar to this, where I will give you an equation. You will not have to write the equation out yourself or anything like that. I will give you an equation, and it will be up to you to decide what's being oxidized, what's being reduced. And so you'll have to determine, again, using the oxidation numbers, what's being oxidized and what's being reduced. And they'll be fairly simple. I won't give you something like this one where there's, let's see, 1, 2, 3, 4 different atoms that you have to work out on each side, so 8 different things that you need to determine the oxidation numbers of. It'll be simpler than that, just because I don't want you to spend 10 minutes on one problem. Alright, so that is redox, and those are the possibilities for redox. Now let's talk about what is apparently everyone's favorite topic, which is the stoichiometry. So we started off here talking about pizzas and using that as an analogy for a chemical reaction. I'm not going to go through all those analogies again, but essentially what we're getting at through this whole section is what stoichiometry is using this balanced chemical equation to take information for one part of a chemical reaction and use it to determine information for another part of the chemical reaction. And so we did some examples here, and like I said, we'll do more examples once we finish here. But this slide here is really the heart and soul of stoichiometry, is this three-step process here, going from the mass of one thing to the mass of something else. So you can have things tacked on to this three-step process, but this, like I said, really is the heart and soul of stoichiometry. Is if you have information about one thing, determining information about something else using this process of converting to moles, using the balanced chemical equation to go from moles of one thing to moles of something else, and then using the molar mass again to convert back into mass. So this is where we'll come back to later. Okay, so here's just more examples here. Now we're going to get into talking about limiting reactants and theoretical yields and percent yields, and so this is just more about percent yields here. And so this summary here at the end is kind of a good thing to go over if you're just trying to remember everything that we talked about there. But the basic idea here is that, well, actually, let me rephrase this. So on the exam, there will be stoichiometry. Some of it will be a little bit more complicated than other parts, but there will be one question where you will have to determine the percent yield, and there will be another question where you'll be finding limiting reactants. If this was an on-campus class with a paper exam, and it was easy for me to see that the work that you do, I would have you do everything in one problem. So I would give you something similar to this, or maybe similar to this, but with a percent yield thing included. But since this is an online exam and there's not really a good way for me to see everyone's work for partial credit, I tried to split the work up. So instead of having everything in one question here, it's split up into multiple questions. So the questions where you're determining percent yield, I will give you all the information that you need to determine that. So the percent yield is not going to be determined using an actual yield and a theoretical yield that you work out yourself. It will just be given to you in the question. So the question will be something along the lines of, this reaction is occurring, the theoretical yield is determined to be this, and the actual yield was found to be this. What is the percent yield? And so I'm just trying to limit the total amount of work done on any one problem, because what will often happen with those types of questions in a paper exam is when there's multiple steps like that, where there's not only 3 or 4 different conversion factors just to determine the limiting reactant, but then once you have that, then plugging that number into the percent yield, there's multiple steps there where if you make a mistake early on, then it just cascades through everything else. And so even if you do everything else correctly, because you started with a bad number, everything else ends poorly. And so I'm just trying to limit the amount of those kind of mistakes that can happen, trying to limit the amount of cascading failures, so to speak, that happens just because you make a mistake early on and that affects everything else. So by breaking it up into smaller pieces, hopefully we can avoid that. So like I said, there'll be questions, or at least one. I don't remember if I put in more than one, but there will be at least one question where you will be asked to determine the percent yield, and you'll be given an actual yield and a theoretical yield. And there will be another question or two where you will have to find the limiting reactant. So I will give you something along the lines of this. So something similar to this question, where all you were trying to find was the theoretical yield, and if you remember, the theoretical yield and the limiting reactant are found at the same time. When you know one, you know the other. So there'll be a question kind of similar to this one, where I'll give you a reaction, and you need to find the theoretical yield or the limiting reactant, just depending on what I ask you to find, but again, you find them both at the same time. And there'll be another question where you will find the percent yield, and it will not be related to the other question. It'll be a completely different reaction, but you'll need to be able to do both. Solution stoichiometry, essentially the same thing here. I'm not going to go so far as to guarantee that there'll be a solution stoichiometry question, but I believe I did put it as a possibility on there, just depending. I really should have gone back and looked over that. Again, it's been a little while since I made the exam. I know it was not a 100% sure that it was going to be on there, but you should know how to do solution stoichiometry either way. Whether I guarantee it's on there or not, you should know how to do it. And again, really the only difference between the stoichiometry that we did on the previous slides and solution stoichiometry is this first step, and possibly the last step too if you're converting into volume. It's just the way that you get to moles is different, and so we use the molarity to do that instead of the molar mass, and that's really the only difference, is how you get to moles and how you get out of moles. All right. Titrations, don't worry about those. I'm not going to test you over titrations on the exam. That is not something that is on there. Okay, let's talk about Chapter 5 real quick. So Chapter 5 is all about thermochemistry and energy and heat. This stuff here at the beginning is not something that you really need to focus in on a whole lot, but you should, at the very least, just kind of remember where energy comes from. This is kind of something that I drove in the lecture, and then I kind of drove it in again on the discussion board, if you've done that discussion board, which I believe was due yesterday, so hopefully you did do that discussion board. So we're just talking about different kinds of energy. I'm not going to be testing you on like the names or definitions of different kinds of energy. This is again just kind of introducing us to the idea of energy and the idea that there are different kinds of energy, and you can convert from one type of energy to another and move it around, which was the conservation of energy, which you should know. You should know at least a rough definition of the law of conservation of energy. And so it just states that energy can't be created or destroyed. That is the first law of thermodynamics, which you could be seeing on the exam. If I remember correctly, I went through and made like just some random true, false, and multiple choice questions from random little tidbits throughout the chapters, and so you could see some of those, something like that. So it could be a true-false question. The law of conservation of energy states that energy can be created or destroyed. Like that is false. It's the opposite. Alright, so here we're just introducing the idea of system and surroundings, that energy can only be transferred from one to the other. Here we're talking about units. You should, by the way, know how to convert from one unit of energy to another. I do believe I put some questions on there where it's just a unit conversion. So it's just, here's a certain number of joules. How many calories would it be? So just converting from one unit of energy to another. You should know how to do that. And by the way, I mentioned this in the lecture, but I'll mention it here as well. If I intend for something to be a big C calorie, capital C calorie, I will say food calorie. So if it just says calorie and it is capitalized, do not assume that I'm trying to trick you and say, oh, it's a capital C calorie. No, if I mean for it to be a food calorie, it will say food calorie. So if I start a sentence with the word calorie for some reason, Not sure what sentence that could be, but if it's capitalized just because it's the beginning of the sentence, I'm not trying to trick you or anything like that. If it's just calorie, then I'm talking about this calorie. Okay, so here talking about internal energy. I don't believe there's any questions where you're using this equation here. What's more important to me is that you understand what a state function is. So you should understand generally what a state function is. So this is any function, any mathematical function, where the function itself is only dependent on the starting point and the ending point of the process, where you start and where you end. The pathway in between is irrelevant. Energy diagrams. These are very useful, but I'm not going to have you drawing them out or anything like that. As long as you can read an energy diagram, you should be fine. You should know how to use this equation as well. I believe I did put some questions in the exam where you use this equation, but I'm not 100% sure. But I believe I did put in some where you would need to use this equation. Thankfully, this equation is really straightforward. The only thing that is a little bit tricky sometimes is, again, making sure you have the correct sign for the heat and the work. Making sure you know whether the heat is positive or negative and the work that's being done is positive or negative. But other than that, it's just add two things together. So not mathematically challenging. As long as you get the correct sign. Okay, this is more the same stuff here, talking about work and heat, and how they are, when you put them together, they give you internal energy, which is a state function. Alright, so this is more just leading into this equation. So these slides here, there's useful information here, and we talked about it a decent bit in the lecture, but they really are just kind of leading up to this equation. The Q is equal to mc delta T equation, which you most definitely need to know how to use because it is on the exam. And I believe there's 2 or 3 questions that you'll have on the exam that cover these, that use this equation. So you should be able to use this equation and essentially just solve for any part of it. So I will give you in the question all the information to have 3 of these 4 things, Q, M, C, and delta T. So you'll have enough information to determine 3 of them, and you'll have to solve for the 4th one. So definitely know how to use this equation. And I don't remember if I included C values in the questions or not. So I would definitely have the that table with the specific heats handy when you take the exam. I think I did, but I'm not 100% sure. I really should have reviewed the exam before I started this. I apologize for that. Should not have thought that I could remember everything after. Wow. So like I said, I would have this handy. I don't think I put anything on the exam that's not on this list here. Unless the point of the question is to find CS, and then I wouldn't have put it on there, but I wouldn't have done something that's on this list. But if you're expected to find the specific heat, it should be on this list. Alright, so this is just talking more about thermal energy transfer. So there could be a question on the exam similar to this one, where you have 2 things that are interchanging energy. So one thing is losing heat, and that heat is going to something else, but I will say that it will not be like this question. So if you remember from the lecture, this question took up the whole page, like it was a big question, not necessarily because the concept was difficult necessarily. It was more just that there was a ton of algebra. The mixing together of multiplication and subtraction and just the order of operations and needing to, like, it was a lot of algebra to get to the final answer here. There will not be a question like that on the exam. If I give you a question like that on the exam, it will be fairly simple. It would essentially just be one equation like this, where you would maybe need to solve this equation for the heat or something like that, but then the answer that you would give would be, so let's say this was the heat of the solution. So you have information for the solution, and you work out what the heat change for the solution is, but then the actual question is asking you, what is the heat change for the metal? You know, if it's a piece of metal and a solution that are exchanging heat. And so the only really extra thing that you would be doing there is just taking the heat for the solution and, you know, giving the opposite sign. So if the solution gained 500 joules of heat, then the answer would be negative 500 joules because that's what the metal would have lost. So I won't do anything too terribly complicated, again, just because those types of questions, number one, are very long, and I don't want you to spend 10 to 15 minutes on one question on the exam, because there's just not time for that. And also because I don't have a good way of seeing the work that you do, I can't give partial credit properly anyway. If it was a paper exam, maybe I'd have you do that, because then I could see the work that you did, and if you made a mistake early on, I could say, okay, there's one little mistake there, but all the rest is fine. Only take off a little bit. But with the situation as it is, I just can't do that. So I'm, again, trying to keep the questions as simple as possible while still making sure that you know the material, which is a fine line to tread. As far as pressure volume work, as long as you know how to use this equation, you should be fine. It is a possibility on the exam, but I'm not going to go so far as to guarantee that you're going to have a question over that on the exam. But again, thankfully, this is a really easy equation. It's just the work is equal to pressure times the change in volume, or negative pressure times the change in volume. So it's a really simple equation. So know how to use that. Bomb calorimeters, don't worry about that. I'm not going to test you over bomb calorimeters. Enthalpy is really just an extension of our discussion of heat from earlier in the chapter. You don't have to know all the derivation of enthalpy and where it comes from and how to get that. Really, all you need to know is that exothermic reactions are when we have negative enthalpy, which means that heat is being released, and that endothermic reactions or enthalpy is positive, so heat is being absorbed by the system. So it is very, very closely related to heat, but it is not technically exactly the same as heat. So again, the big thing here is being able to identify an exothermic reaction versus an endothermic reaction. So there could be questions on the exam where I say, here's a reaction, and I describe the reaction, and I give you enough information in the description that you should be able to tell if it's an exothermic or endothermic reaction. And that could just be me saying that the reaction gives off heat, which would indicate that it's exothermic. Or I could even go so far as to say delta H is positive. Is it endothermic or exothermic? Well, that would be endothermic, because the delta H is positive means that your system is gaining heat. It's sucking heat in from the surroundings, and so that would be endothermic. All right, so this is just more about enthalpy, and so then the last thing in this chapter was determining enthalpies of reactions. And so we had a few different ways of doing that. There was actually going and doing a reaction in the lab to determine the enthalpy of a reaction. And again, just if we were doing a paper exam, I would feel like I could put a question like this. I really like this one, although I'd probably make it a little bit simpler. This one is a little bit wordy, at least. But just because this is an online exam and I'm very limited in what I can C of your work. Really all I can see is the answer you give. I don't feel like I can give you a question like this where there's multiple steps and really feel good about giving you that question, because these questions are multi-stepped processes. Not only are you doing the Q is equal to MC delta T, but then you have to relate that to the reaction, and then you have to do what is essentially stoichiometry as well, relating how many moles of stuff that reacted to that number of joules, usually, of heat that's released. So there's not going to be a question like this one on the exam. I wish I could, but I can't justify it, putting that on there, just because that would be it would be a tough question for sure. But what I can put on there is something that is either from Hess's law, where you take multiple different reactions, manipulate those reactions, add them together, flip them, whatever you need to do to get the goal reaction, and therefore the enthalpy that you're looking for, or the standard heat of formation, because remember these are two different methods that give you the same thing. So Hess's law tells you the enthalpy of a reaction, and so does the standard heat of formation. So Hess's law, I think, is a little bit more troublesome to use, and it's a lot more troublesome to write questions for. So unfortunately, this is again a situation where if we were having a paper exam, things would be slightly different. If we were having a paper exam, all I would tell you was, I will give you a question where you either use Hess's law to find the enthalpy of a reaction, or you will use standard heats of formation to find the enthalpy of a reaction. I'll give you one, but not both. And so you would have to make sure you know how to do both. But unfortunately, with these online exams, there's not really a good way to do Hess's law. Short of trying to go on the internet and find images of those, it doesn't really work very well. So you will be doing standard heats of formation on the exam. That is much easier to do. I can just give you the reaction, and then you will be expected to look up the values in the appendix. So the values will not be listed in the question itself. You'll be expected to have the book handy, or the PDF of the book handy, so that you can look up those numbers and plug them into the equation here, the sum of the products minus the sum of the reactants. And you will be doing that on the exam, so make sure you know how to do that. And that is the end of Chapter 5. So the last one here, Chapter 9, gases. Here at the beginning, we're just talking about gases in general, but I do expect you to know these assumptions that we're making here with the kinetic molecular theory of gases. More specifically, they're going to come into play later when we talk about how some of the assumptions are not completely correct. So you do need to be familiar with these basic tenets of kinetic molecular theory. So here we're just talking about gas pressure. Let's see, it's kind of an introduction to the idea of where gas pressure comes from. I'm not going to test you over the anatomy of the ear. I'll let your anatomy teachers do that if you take anatomy at some point. I'm also not going to test you over barometers and how they work. But I do expect you to be able to use these conversion factors to convert from one unit of pressure to another. I did put some questions on the exam where you do something similar to that. I think I made a pool of questions where it was just some random energy and pressure unit conversions. So So do know how to convert from one unit to another. Also, know how to use the three, I believe we talked about, 3 simple gas laws. Technically there's more than 3, but we only talked about 3 of them. So Boyle's law, Charles's law, and Avogadro's law. Know how to use all 3 of those. What I mean by that is be able to take the equations for those 3 simple gas laws and solve for any part. These are fairly simple equations. The only thing that tends to trip students up is sometimes the algebra is a little bit different. Like if you're trying to find N1 here, just because it's in the denominator here, there's a little bit of algebra that has to be done to get it to where you can solve for that. So just review your algebra to make sure you know how to do that. But really, other than that, just understanding the basic relationship between these, know which ones are directly proportional, which ones are inversely proportional, which would be Boyle's law. That's an inverse relationship. As pressure goes up, volume goes down. The other 2 are directly proportional, so Charles's law, as the temperature goes up, volume goes up, and Avogadro's law, as the number of moles goes up, the volume goes up. So that is also directly proportional. So just be familiar with those 3 simple gas laws because you will be asked questions over those. The way that I made those questions, I don't believe I set it up to where you would for sure get a question over each of those. I think the way that I had it set up is I made a pool of like 7 or 8 or something, just random questions over these simple gas laws, and then I told the exam to give you 2 or 3 of them, something like that. So be sure you know how to use all 3 of those. And be sure you know how to use the ideal gas law, because once again, I guarantee you will see questions over the ideal gas law on the exam. So know how to take this equation and solve for any one part of the equation. Okay, let's see here. STP, standard temperature and pressure. I would suggest that you be familiar with this, just so you don't have to go and look it up on the exam, because there were 1 or 2 questions where I did stipulate that the reaction was occurring at STP. So it's not something you necessarily have to memorize, because you can look it up since you're taking the exam at home. But you should be familiar with it beforehand, so you're just not, out of the blue like, what is he talking about, STP? So 1 atmosphere pressure, 0 degrees C, or 273 K is STP. So just be prepared for that if you see it on a question. Alright, the molar volume that it's talking about here, this is again just something that's kind of a handy shortcut if at some point you need to use that. It can be helpful, especially for gas stoichiometry problems. If you know how many moles of gas you have at STP, then you can use that to very quickly and easily figure out how many liters that would occupy. As far as the density of gases, I do expect you to be able to use this equation, just in the same way that I expect you to be able to use the ideal gas law. We should be able to use this equation, which describes the density of a gas, and to be able to solve for any part of that, given enough information. And just to remind you here, this fancy looking M, that is the molar mass. So the molar mass is included in that equation. Alright, there's just more there. Mixtures of gases. These were pretty straightforward. It's just talking about how if you have a mixture of gas, you can treat the mixture of gas as if it's just one gas, because all gases behave essentially the same. But if you do want to split them out, you can do that using Dalton's law. So you can split them out into their individual pressures. This is something that you should know how to do, but I'm not going to go so far as to guarantee that that's going to be on the exam. but you should be able to, if I have a mixture of gases, kind of similar to what we did here in this question, you should be able to split them out one from the other and solve for just one part of it. And kind of similar to what I talked about in previous chapters, I'm not going to make a question like this super complicated where it should take you 15 minutes to solve it or anything like that. It'll be straightforward and shouldn't anyway be terribly time consuming. As far as collecting gases over water, don't worry about that. I'm not going to test you over that. So there's no need to have this table here handy. If at some point you work in an industry where you do collect gas over water, you will carry this table around with you all the time to help you with your calculations. But for now, we're not going to worry about that. Reactions here, doing stoichiometry with gases, similar to what I said with the solution stoichiometry and just stoichiometry in general. I'm going to do my best to keep this as simple as possible. If you have this, again, I'm not going to go quite so far as to guarantee that there will be stoichiometry with gases, but if you do come across stoichiometry with gases on the exam, it'll be fairly straightforward. I'm not going to try and do anything tricky. If at some point you come across a question and you think, oh, I think he's trying to trick us here, no, I'm not. I'm not trying to trick you. I'm going to keep it as straightforward as possible and try to keep it as simple as possible, again, while still making sure you know how to actually do the process. So again, the main difference here is just how you get to moles. That's the main difference between this kind of stoichiometry and the normal, so to speak, stoichiometry. Is just when you're dealing with a gas, you would need to use the ideal gas law in order to work out, given the pressure and volume and temperature of a gas, how many moles of gas you have. Alright, so it's just more of that stuff there. So then the last bit here, don't worry about the velocity distribution. Really well, I guess I should say, that I do expect you to know that bigger molecules move slower than smaller molecules. So the smaller the gas, the faster it moves. And that's really all I expect you to know from this. So oxygen is the biggest element, the biggest molecule on this list, and so overall it is the slowest. Hydrogen is very tiny, and so overall it is the fastest. That's all I expect you to know from that. But I'm not going to have you doing anything with these equations or anything like that. Just knowing big stuff moves slower, small stuff moves faster. And then the very last thing here, talking about the assumptions that we made and how some of them break down. All I expect you to know from this section here is that at high pressure, the assumption that the molecules of gas take up no space breaks down, and at low temperature, so then at low temperature, the assumption that the gas molecules don't interact with each other breaks down. So if you remember from way back at the beginning of the chapter, and actually one of those I think I forgot to write down here. Yeah, so there's, and I think in the video I did manually write it in here, but there's this assumption here: gas particles neither attract nor repulse each other. And then there was another one that hopefully I wrote in. It's been a while since I made that video, but I believe I wrote in the other assumption, which is that gases occupy no space. And so that's the last thing I expect you to know from this chapter is just the two situations where those assumptions break down. So again, just to reiterate, this assumption, this breaks down when you're at very low temperatures. So the molecules are moving slow enough, they have a small enough amount of energy that when they smack into each other, they stick a little bit more than they should or would otherwise. So if they're moving really fast, they hit each other so hard that they can't really stick to each other at all. They really do bounce off of each other elastically. But if you slow them down enough, they stick a little bit. And so they don't behave ideally because of that. And then the other assumption, which is that gas particles take up no space, that assumption breaks down when you are at very high pressure. So at very high pressures, the particles are packed in so close to one another that they are actually occupying a significant proportion of the overall space in the container. And so that assumption is no longer valid in that case. All right. So that is it. There was one last graph there at the end. Oops. That I think even in the lecture videos I just said don't even worry about this. I should just delete that actually because it's not terribly useful. So that is it. I'm not going to have you working out equations like this one here. I know some professors actually do. Even here at TCC, some professors have their students like work through this whole modified ideal gas law, which I mean is fine. It's not a terrible equation. It's not terribly hard to do. It's just kind of tedious, and you end up with answers that are not really all that different than if you didn't use the corrected version. So you're not going to be doing that. Are there any questions over those lecture slides?
None so far. But I do have a question regarding the PowerPoint slides themselves. Are you going to be uploading those?
Yes, they are up now actually.
Okay.
Yeah,
I haven't checked yet. So.
yeah, I put those up earlier this morning. For some reason, I thought I had already put up Chapter 9, and obviously I had not, and I apologize for that. That was just an oversight on my part. But they are up now, along with the rest of them. So 6, 7, and 8 are also up now as well. So
Okay.
all the rest of the lecture slides are up. All the labs should be up and available. I think there's only one discussion board that I haven't written yet, but I got a couple written yesterday. So the discussion board for this week is up and available, and the last discussion board is up and available. I still need to write the one for next week, or 2 weeks from now.
I do have one question.
Mm-hmm.
So technically is the theoretical yield and the limiting reactant in relation are the same thing, correct? Because you said that if we found one, we would find the other.
So they're not the same thing, but you find them simultaneously. So the theoretical yield is an amount of product that can be made. The limiting reactant is the reactant that is used up in making that amount of product. So they're not the same thing, but they are inextricably linked. They're linked to one another, but they're not the same thing. Does that kind of make sense?
Yes. You use the limiting reactant to find the theoretical yield.
Yes.
Okay.
Yeah. So if you know the limiting reactant beforehand, then yeah, you can just take that one thing and say, okay, if all of this reactant is used up, how much product can I make? In the questions that we didn't know what the limiting reactant was beforehand, and so we had to figure that out. But there will be some times when you do know the limiting reactant beforehand. And I think actually 1 or 2 of the practice problems we did in the lecture, we were told in the problem, we have these 2 reactants, but we have more than enough of this one over here. So we didn't actually state it that way, but essentially what that was telling us was this other thing is going to limit our reaction. So the other thing would be our limiting reactant. So let me see if I can find a good example of some stoichiometry here. I'll use a different book. So maybe I can get a good example from that. Okay, here we go. Let's do this one. Okay, so just let me pull up something slightly different here. I don't really like writing in the Blackboard application here because it's always trying to autocorrect my drawing, which is annoying. So we're going to do it here instead. Okay, so this is a question from a different book. So we have a chemical reaction here that is magnesium hydroxide, which is the active ingredient in milk of magnesia, which is used as an antacid. When it reacts with HCl, which is stomach acid, we have this reaction taking place. So the question says, how much HCl in grams can be neutralized by 5.5 grams of magnesium hydroxide? So if we have 5.5 grams, and actually let me move that just a little bit. Let's move it all the way over here. So we have 5.5 grams of the magnesium hydroxide, and we want to know how much of this other reactant can be neutralized by that amount of magnesium hydroxide. So this is a stoichiometry problem, only in this one we're not relating an amount of reactant to an amount of product. Instead, what we're relating is one reactant to another reactant. And that's perfectly fine. We can do that. We don't have to relate reactants to products. We could relate products to products. It doesn't matter. As long as we have our balanced chemical equation, we can relate any one part to any other part. And so what we're trying to do here is the process that was described in these slides, where we go from the mass of something to moles. So this would be the mass of A to moles of A to moles of B, and then mass of that second thing. So we're starting with the mass of the magnesium hydroxide, and we're trying to figure out what mass of HCl would get used up if all of this reacted. And so just like any stoichiometry problem here, if we're going from the mass of something to mass of something else, These three steps are always going to be the same. The only difference is going to be what are the molar masses of each thing and what is the ratio here between the number of moles, which gets into both of the questions actually that we had at the beginning of the video. So for this step here, going from mass of one thing to moles of something else, we're going to be using the molar mass of A, which would be the magnesium hydroxide. Going from moles of magnesium hydroxide to moles of HCl, we're going to be using the ratio between these two, which is a 1 to 2 ratio. So for every one magnesium hydroxide that reacts, it uses up 2 HCl's. So we'll use that here in our series of equations, series of conversion factors. And then the last one here is the molar mass of the second thing, the molar mass of the HCl. So if we go ahead and start plugging these in here, the molar mass of magnesium hydroxide, I do not know off the top of my head. You add that up real quick. So magnesium is 24.31. Hydrogen is essentially 1.01, and we have 2 of them. And oxygen is essentially 16, and we have 2 of those. So that gives me the molar mass of my material is 58.33 grams per mole. So grams for every 1 mole. I want my grams to disappear, so I'm going to put grams on the bottom here. Again, this is for magnesium hydroxide. So by putting grams on the bottom, the grams here are now canceled, and I'm left with moles. So that was my first step. So now I've gone from the mass of it to the moles. Now I want to go from moles of magnesium hydroxide to the moles of HCl. And to do that, I use the coefficients in this balanced equation. So this balanced equation tells me that for every 1 mole of magnesium hydroxide, I use up 2 moles of HCl. So when you're doing this step, you're just taking whatever the number is in the coefficient here and just plugging it in. And just remembering that if there's no number, then it's assumed to be 1. So we had 1 and we had 2. So now my moles of magnesium hydroxide are gone. And I'm left with moles of HCl, but the question wanted to know how many grams of HCl would get used up. And so I have one last conversion to do here. Chlorine is 35.45, and hydrogen is a little over 1. Not sure why I needed to get my calculator out to do that, but so I have 1 mole of HCl is the same as 36.46 grams of HCl. And it's perfectly fine that we had 2 moles of HCl here and 1 mole of HCl here. The only thing that's important is that the units match up. If you really wanted to put 2 moles of HCl here, you could, just as long as you then put the number of grams that would be in 2 moles of HCl, which would be I guess it'd be 72.92, I guess. Whatever 36.46 times 2 is. So the moles of HCl cancel, leaving with grams of HCl. And if I do all the math here, so I'm going to take all the numbers on the top of the fractions and multiply those together, and then divide by everything on the bottom, which is just one thing there. So 5.5 divided by 58.33 times 2 times 36.46. My milk of magnesia there would neutralize almost 7 grams of HCl. So in this particular question, we weren't looking for a limiting reactant or a theoretical yield, but we could tack on that to the question. So we could, let's see, we could try to find the theoretical yield of magnesium chloride from this. So if we wanted to find the theoretical yield of magnesium chloride, given that magnesium hydroxide was the limiting reactant, it would be essentially the same type of thing here. We would start out with 5.5 grams of the magnesium hydroxide. We would convert that to moles. But the difference would be at this point, because we're no longer trying to figure out how much HCl is used up, if we're trying to find the theoretical yield of magnesium chloride, we would now be looking at this molecule instead. So instead of converting from moles of magnesium hydroxide to moles of HCl, we would convert from moles of magnesium hydroxide to moles of magnesium chloride. And that is a 1-to-1 ratio. We have one of these for every one of these. So we have 1 mole of magnesium hydroxide for every 1 mole of magnesium chloride. And so then we would have one last difference here, which we would need the molar mass of MgCl2 instead of HCl. And again, I don't know that off the top of my head. So 24.31 plus 35.45 times 2. So chlorine is 35.45. We have 2 of those. So for every 1 mole of MgCl2, we would have 95.21 grams. And again, this just came from the periodic table. I just took the numbers from the periodic table. 1 magnesium, 2 chlorines. So if I check my units here, grams of magnesium hydroxide cancel, moles of magnesium hydroxide cancel, moles of magnesium chloride cancel, and that leaves me with grams of magnesium chloride. So if I do that math, my theoretical yield of magnesium chloride would be 8.98 grams. All right. Does that at least answer some of your questions?
Yes. For me, I guess the part that really confused me was where to get the ratio part.
Mm-hmm. Yeah, that is always just going to be from the balanced chemical equation. So in the in the example we had here, you're just going to be looking at what 2 things am I comparing? What am I going from? What am I going to? And the ratio is always just going to be the coefficients from those 2 numbers. So take the coefficient for the magnesium hydroxide here, which was 1, and the coefficient for the HCl, which was 2. It is always just those numbers. And so it's always just going to be simple whole numbers as well.
Okay. And on the exam, I was taking notes, but you mentioned that, or are we gonna have any questions dealing with uh, solutions geometry?
It's possible,
Specifically
yes.
dealing.
That is
Okay.
a possibility. I don't remember if that was one of the questions that I required or if I just put it in a pool with other types of stoichiometry questions. But it is definitely a possibility. So for
Okay.
solution stoichiometry questions, we could do an example of that real quick.
Yeah.
Let me see if I can make one up. Let's say, well, yeah, it'd probably be easier just to make one up. Think of a good reaction. Good simple reaction. So it's going to be kind of similar to the last one that we looked at, but oh well. All right. So we have a reaction taking place here that is the same type of reaction as the last one that we saw, but it is different molecules, and we're going to be looking at a volume of this stuff instead of a number of grams. So let's say, and actually we'll combine, we'll throw in some limiting reactant and theoretical yield stuff in here as well. So let's say we react 20 mils of 0.20 molar calcium hydroxide and 15 mils of 0.15 molar HNO3. And I want to know what is the limiting reactant and the theoretical yield of, yeah, why not, water. Normally you wouldn't be interested in how much water is made, but we'll go ahead and figure it out. What's the theoretical yield of water for this reaction? So this question is more complicated than what I would put on the exam. Most likely on the exam it would just essentially be one of these. Like I would have maybe just this section where I just say, you have this much stuff reacting, how much water is made. I wouldn't give you both, just because it's a whole lot of work, and there's lots of points where you could mess up there and have it cascade through the rest. But since we're here working through it together, I think it's fine to have everything included here essentially. So what we're going to do here is we're going to have two separate conversions that take place. We're going to figure out, given this amount of calcium hydroxide, how much water is made, and given this much HNO3, nitric acid, how much water is made. And whichever one is less, whichever one is smaller, that will give us the theoretical yield. So we're going to start out here with our 20 mils of, and I'm just going to say B because it's a base, because I don't want to write out calcium hydroxide every time, and 15 mils of the acid, which is nitric acid. So we're starting out with different volumes of two different solutions. So if you remember, our goal here is going to be to get from the volume to the number of moles, and then get from number of moles to moles of our product, which is water in this case, and then we'll convert that into grams of water. So we're only going to be doing one solution thing here, because I didn't ask for the number of milliliters of water that are produced. I just asked for the I didn't specifically write it down, but I want the mass of water that is produced. And it's perfectly fine to mix them in like that, where one of them is a volume conversion and one of them is a mass conversion. Alright, so if you remember this step here, to get from volume to moles, we use molarity. This step here, we're going to use the ratio, just like we did in the previous kind. This step here never changes. No matter what kind of stoichiometry you're doing, whether it's solution stoichiometry, mass stoichiometries, gas stoichiometries, this ratio is always going to be the same thing. It is always just the balanced chemical equation going from one molecule to another. And then this step here is the molar mass of water. So to use the molarity for this first step, we do actually have one thing we need to do first. Because if you remember, molarity is the number of moles divided by the number of liters. And we do not have liters. We have milliliters. So we do actually have one step here at the beginning that we need to do first, which is to convert from milliliters into liters. And if you remember, there's 1,000 milliliters in a liter. So if we go ahead and do that conversion, actually let's go ahead and we'll leave that there, we won't do the math yet. So that will convert us from milliliters into liters. Now we can use the molarity. And we're going to plug the molarity in just like we would plug in the molar mass. So we're just going to flip it whichever way we need to get the units to cancel out correctly. We want the liters to go away, and we want to keep the number of moles. And so we are going to plug in the two molarities with liters on the bottom and the number of moles on the top. So we have 0.2 moles for every 1 liter and 0.15 moles for every liter. Does that step make sense?
Yes.
Okay. So once we have this step, you can see here now that our liters and milliliters are canceled at this point, so we're in the number of moles, so we are here. So now we can go back to our normal, so to speak, stoichiometry and just plug in the ratios. So for the calcium, which was the base here, that is a 1 to 2. So for every 1 mole of the base, there were 2 moles of water produced. For the acid, it was a 2 to 2. For every 2 moles of acid that are used up, you make 2 moles of water. Again, we're just taking those coefficients and just plugging them in. So we had 1 and 2, because we have an invisible 1 here and 2, and we have 2 and 2. So then the last one, last conversion factor for each of these is for every 1 mole of water, there's 18.02 grams of water. And again, that number just comes from the periodic table. It's just I've done water so many times I don't have to look at all that. All right, so we have a whole bunch of math here to do. So if we multiply everything on the top, divide by everything on the bottom for that for the base, we get 0.144 grams of H2O. Really, technically, with sig figs, it'd just be 0.14, but I'm not super worried about being that accurate with sig figs at this point. And then for the bottom one here, 15 divided by 1,000 times 0.15. The times 2 divided by 2 is going to cancel each other out, so I'm just not going to bother with that. And this made 0.041, we'll say, grams of H2O. So, when we're answering the question here, we now have all the information to determine what is the limiting reactant and what the theoretical yield is. But again, they are two different things. So the limiting reactant is the reactant that ran out first. And that would be the nitric acid. So you can either say 15 mils of HNO3 is the limiting reactant, or even you could just say HNO3 is the limiting reactant. You don't necessarily have to specify the amount. But the acid is the limiting reactant, but the theoretical yield is not 15 mils of HNO3. The theoretical yield is how much of the product is made when the limiting reactant is used up. And
Right.
so the theoretical yield is 0.041 grams of H2O.
Okay.
Because once you've made that much water, there's no more acid. The reaction can't go on any further. Does that kind of make sense?
It does.
Okay, so it is a little bit confusing because you do find them simultaneously and they are related to each other, but they are not the same thing. All right, any other questions about that stuff?
Will we have something similar to the question like in Lab 5 regarding the transfer of heat through two solutions? The post-lab problems, 12 and 13.
Let me pull that up real quick.
Oops,
So
sorry about that.
I vaguely remember that question, but I want to... no. No, there won't be a question like that.
Okay.
So that question, it's something that I hope you were able to work through on the lab, but this is another example of a question where it's like there's nothing in there that you shouldn't be able to do, but there's quite a few steps in that process, and I don't feel like I can justify putting in a question like that where
Yeah,
I can't
there
see
were
the
a
work
lot
that
of
you've done.
steps to finding the solutions to the questions. So
Yeah, so like the and 13 was related to 12. So like in 12, it tells you the amount of stuff that you use, and so there's some stoichiometry that you have to do in that part to figure out how much enthalpy is created, essentially how much heat is released by this reaction, and then that leads into part 13 or question 13, where once you know how much heat is released, how much will the solutions heat up, so how much will the water heat up, essentially. So that's, yeah, it's a multi-step process. Any one of those individual parts, that is totally possible on the exam, but a question like these where they're all together, that's just a bit too intense.
Okay.
Anything else?
No, that is it for me.
Emma, do you have any other questions?
No further questions. Thank you so much for your time.
Yeah, no problem. Thank you both for showing up. And I'm forgetting already the person that was here earlier. But I guess I had to leave. Thank you as well for showing up. And those of you that are watching this later, feel free to email me. And I guess those of you that are here now as well, if you come up with a question later, feel free to email me. And I will do my best to get back to you promptly. The exam will become available tomorrow. I know last time I made it available on a Tuesday, but I decided to change that just a little bit. So it'll be available tomorrow, and it'll be available until the normal time on Sunday. So I just wanted to be absolutely sure that everyone had plenty of time to watch the video before the exam was available. So I'll have this video uploaded. It'll probably be an hour at least, just because it takes a while for the video to process. But it'll be up this afternoon at some point. All right. If there's nothing else, I think I'll let you all go. Good luck studying for the exam, and I will hopefully talk to you next week.
All right.
Thank you.
See you next week.
Bye.